All right, and welcome back. So today we are going to be talking about exponential growth and exponential decay. This is part of Chapter 9 of our Algebra 1 curriculum here. So again, today we are going to be talking about what are some of the characteristics of exponential growth and exponential decay functions. Well, first let's start out with exponential growth functions. Please copy down this set of notes as we are going to be discussing it in just a moment. So a function that's of the form y is equal, or sometimes f of x, is equal to a times 1 plus r raised to the power of t is an exponential growth function. And there's two main things that have to occur. A has to be greater than 0, so our initial amount has to be bigger than 0, and the rate of growth has to be bigger than 0. So remember, this is in growth. So if our r is negative, then we're not going to be growing. We're going to be getting smaller and smaller. So we need that r, or that rate of growth, to be positive. Now, sometimes you're going to see, a 10% growth. Well, when we use our formula, the rate of growth, it says has to be in decimal form. So if it's not in decimal form, we have to translate it. So if I had a 10% growth, I'd have to write it as 0.1 or 0.10. Sometimes you might see something that looks like this. Y is equal to, 1, 2, 3 times 1.35 raised to the t. And this is a simplified version of what you see above it. The growth factor, what we call 1 plus r, is actually right in here. And we can rewrite it as 1 plus 0.35. So our rate of growth would be 35%. Rate of growth would be 35%, because if we took 1 plus r and we know it's going to be 1.35, well then we know that my r is going to be 0.35, and if we want to put that into percentage, we have to change it into a percentage, so we just move the decimal place twice. Okay, so let's show a couple examples with this. So it says the inaugural attendance of an annual music festival is 150,000. That's a lot of people. The attendance y increases by 8% each year. Write an exponential growth function that represents the attendance after t years. So generally, it's y is equal to a times 1 plus r raised to the t. A is our initial amount. R is going to be our rate of growth, and t is going to be the time over, just time, right? The time from when we start to when we end. So we need to fill in some stuff here. Y is not going to change. What is our initial amount? Well, our initial amount is 150,000. So it's going to be 150,000 times now 1 plus, what is our rate of growth? Well, we're growing 8%, so plus 0.08 raised to the t. That's after however many years, right? We're soon going to simplify this as our growth factor of 1.08, but for right now, I just want to list it as 1 plus 0.08 for you to see it better. Part B says, how many people will attend the festival in the 5th year? Round your answer to the nearest 1,000. So we're just going to take our formula, y is equal to 150,000, so our initial amount, times 1.08. I simplified that down to the t, but again it says in the 5th year. So we're going to take this t and turn it into a 5. So it's going to be y is equal 150,000 times 1.08 raised to the 5th power, because it's after 5 years. So you just take out your handy dandy calculator And we can just plug it in. So 150,000 times 1.08 raised to the fifth. You need to include your parentheses here. Everything that you see on the screen, you want to input into your calculator. You want to use the caret button when you do this. So you really should see in the calculator form, you put it over here, 150,000 parenthesis 1.08 caret 5. That's what you want to input into your calculator. And when you do that, it says round to the nearest thousand. So let's write out what we get before we round. 220399, 220399, 0.2, and we want to round to the nearest thousand here. So we go to our nearest thousand, and we're going to leave it as 220,000. That would be our answer. It says round to the nearest thousand, so we rounded down because we look at the 3 is going to determine whether or not we round up or down. And 3 is below 5, so we round down to 220,000. That's a lot of people, but nice job, right? All right, cool. Here we go. It says a website has 500,000 members in 2010. The number Y of members increases by 15% each year. A, write an exponential growth function that represents the website membership's T years after 2010, and B, how many members will there be in 2016? Round your answer to the nearest 10,000. So try out this one on your own, and then resume when you are ready to do it with me. All right, so we are going to write out our formula. So it's Y is equal to A times 1 plus R raised to the T. Let's fill in some information. Y is equal to our initial amount, which is 500,000, times, I'm going to simplify this, it's increased by 15% each year. That's 0.15 as a decimal. So it's going to be times 1.15 because I'm adding it together, raised to the T amount of years. Remember, starting in 2010 here. So this is A. This is going to be our answer for A. For B, it says how many members will there be in 2016? So we're going to take exactly what we just wrote, but we need to change T. So it's Y is equal to 500,000 times 1.15 raised to the T amount of years. A lot of students are going to say, oh, I'm going to put 2016 up here. But that's not how we do it. It says after 2010, and now we're looking at 2016. So we're going to do 2016 minus where we start, and that's going to tell us the amount of years that passed, right? So really, we don't use this. We're going to write 6 because 6 years passed since 2010, and it's now 2016. So we can simplify it down. It says round your answer to the nearest 10,000. Okay, so we're going to do 500,000 parenthesis 1.15 close parenthesis caret 6. I'm just going to write down what we get beforehand. what's that? 5, 6, 530. 0.4. Okay, it says round to the nearest 10,000. So we're looking at for 10,000, that means we have to go to the 1,000 to tell us where we're going to round. That's 1, 10, 100, 10,000. The thousandths is a 6, which means we round up. And our final answer is going to be 116,000, meaning we have 1,160,000 people attending it. All right, great job, folks. So now let's talk about exponential decay. So decay is going to be very, very similar to growth. The only change here is that our rate of decay is going to be less than 1. So it says that r is going to be in between 0 and 1. And that should make sense because if we're less than 1, well then we're doing 1 minus that rate. So if I do 1 minus 0.5, well I'm going to be at 0.5. If I start going less than 0, then I'm doing 1 minus a negative, which really means I'm adding. So that doesn't make sense for decay. Decay is going to be our rate of decay is going to be going down. So we should be seeing a lesser amount. And it's going to be the exact same thing as we've been doing for growth in examples, except instead of doing 1 plus the rate, we're going to be doing 1 minus the rate. So for example, if I just made one right now, if we start out with 1,000 items, I don't even know, 1,000 items, and we have a 10% rate of decay, how many are left in 4 years? So we would write out our formula. Y is equal to our initial amount, which is 1,000, times 1 minus our rate. Our rate is 10%, so as a decimal, it's going to be 0.10 or 0.1. And we want to use our time, t, being 4. So we can simplify it down to 1,000 times 0.9 raised to the 4th. When we do that, 1,000 times 0.9 caret 4, 656.1. So we're going to have 656 items. And that should make sense because we're talking about decay. So we should see a lesser amount of when we start. And you would use this formula for any problem that has decay. Sometimes they're going to ask you though, hey, can you look at a table and determine what's going to be growth or decay? So let's do that. Let's see if we can figure out if something's going to be an exponential growth function or exponential decay function, or maybe even neither. When we're talking about growth and decay, we're always using multiplication. Sometimes people say division, but remember, division is just multiplication with a reciprocal to it. So if we look at A, our x's are increasing by 1, which is good, and our y's, I'm going from 270 to 90 to 30 to 10. Well, if we try and look at it with multiplication, well, I'm getting 1/3 less, 1/3 less, 1/3 less. So this is going to be decay. I have a constant rate of change within, or a constant ratio of change. Sorry, I have a constant ratio of change, which is 1/3. So our decay would be 33%, or 1/3 of it. Actually, it would be 66% because we're left with 1/3. Sorry. So, but now with B, our x's are increasing by 1, which is good. 5 to 10, I'm multiplying it by 2. 10 to 20, I'm multiplying by 2. 20 to 40, I'm multiplying it by 2. So this is going to be exponential growth. All right. So we have 2 more for you to try out. Try out these 2. Pause the video to attempt it and resume when you're ready to see the answers, as the answers are going to be on the next slide. All right, so it says determine whether the table represents an exponential growth function, an exponential decay function, or neither, and then explain. Well, here are the answers. The second one is going to be decay, because we're going from 64 to 16, that's 1/4. 16 to 4, 1/4. 1/4. So we have a constant common ratio of 1/4. And now for number 3, it's actually neither. It's going to be linear. Here's why. Our x's are increasing by 2 by adding by 2, which is fine. But when we look at our y's, we're adding 7. That's our pattern. We're adding 7. And since we're adding, this is going to be a linear function. It's not going to be an exponential growth nor decay. All right, folks, great job. If you have any questions, please feel free to reach out. You're doing so well, and we're so proud of you. Thank you for tuning in. Have a good one.